All right, Kc versus Kp. This is the first of many, many subscripts we're going to put after a K. We're going to see Kas and Kbs and Kws and Ksps. We're going to see all sorts of Ks. The first two subscripts that we see is Kc versus Kp. Okay, so we can write the equilibrium constant expression in terms of concentration, which is what we've done in our previous units. You could also do it in terms of pressure, which we're going to see here in a little bit. So up to this point, what have we done? We've put in concentrations. Those concentrations must be in terms of molarity, and the reaction would have an expression that would be written like this. Here is an example. I've got a reaction. Whoops. Well, let's write it. Let's write it up here. What would it look like? Well, we would have H2, that's a product. It has a 2 coefficient, so it becomes squared. We have S2, okay. It has a 1 coefficient, so it's raised to the first power, which we don't need to bother writing. We have H2S, okay, and that is squared, and this would be our K value. Now, if we go and plug these in, these are concentrations, we designate it with a C. So we were doing Kc values before, but we weren't calling it that because I wasn't bothering you with a designation there. Now we're going to see that we could take this thing and we can, if it's gases, if it's aqueous, that's all we can do, okay? But if they're gases, we can also do a Kp. All right, so here we have a reaction which they are gases, A and B, and we've got our little coefficients, okay? So what we have for this in terms of concentrations, we would use the square brackets. We do products over reactants, and it would look like what you see in the red box. Got a little carried away with too many things popping up there. So what you see in the red box is products over reactants raised to the power of their coefficients. When we look at these, because they're gases, you could also do a Kp instead, okay? So it'd be partial pressures you would put in there. The partial pressure of B raised to its coefficient, the partial pressure of A raised to its coefficients, and that would be a Kp instead. Now sometimes these happen to have the same value, and you will see when that would happen, but they don't have to have the same value when you obtain them for the exact same reaction. Now they should give you the same sort of information. You know, they will both either be really big or both be really small, but they might not be exactly the same number. Now, I told you with concentration, you had to plug these in molarity, okay? We had to use molarity in order to get the right value for K. With gases, and this is easy for students to forget, especially if a problem they're working, they're given it all in torr or millimeters of mercury, you must plug into this equation those pressures in atmospheres. It will give you a different answer in many cases. Some cases it won't make a difference, but in many cases it will make a difference. So you got to make sure you're plugging those pressures in atmospheres instead of anything else. All right, now there's a relationship. Ooh, that says there's a derivation on these pages. I'm going to real quickly scratch that out because I have not looked that up in the OpenStax textbook. We're not going to get into the derivation at this point, but I will kind of give you a hint to the derivation. There's pressure. PV equals nRT, right? That's the pressure. V and N, if I put the V over here, N over V, that's molarity, okay? It kind of plays off of that, and it's what helps me remember the equation. Here is the equation. The Kp value is equal to the Kc value times this RT term raised to the power of delta N. So we need to know what delta N stands for, okay, and we'll look at it here. Well, if we're using this in our derivation, can you figure out which R we're going to need? We're going to need the one that has atmospheres in it, aren't we? So we're going to use that R value, and while Kc and Kp are unitless values, we have to make sure we use the right R here. We know that temperature is going to have to be in what unit? Well, it's going to have to be in Kelvin, of course, okay? And that delta N business, okay, you look at your balanced equation, and you look at the moles of gaseous product and you subtract the moles of gaseous reactant. Delta N, final minus initial, okay? So you're looking at how many moles of gas are on the product side, subtract how many moles are on the reactant side. Let's give you an example. Let's say we have 2A, and that's a gas, going to 2B, that's a gas, plus C, and that's a gas. So delta N would be, well, I have a total of 3 moles of gas on this side, right? 2 of this and 1 of that. And I have 2 moles of gas on this side. So delta N would be 3 minus 2. You would plug that in and you would get exactly the same. I mean, you would be able to get the Kp from the Kc. So when would Kp equal Kc? What would that delta N have to be to make those equal? Well, delta N would have to be 0 because RT, anything raised to the 0th power equals 1, all right? 4 raised to the 0th power is 1. 100 raised to the 0th power is 1. Anything raised to the 0th power is 1. So the R and T disappear, and Kp will equal Kc. So there are times when numerically their values are exactly the same, but it's only when delta N is equal to 0. All right, so that is what we say there. So let's do some problems. All right, let's do some example problems. In this problem, we're going to determine the equilibrium constants Kc and Kp. What are they giving me there? They're giving me moles of each substance, and they're giving me the volume of the vessel. They're also giving me the temperature. So let's start with doing Kc, okay? Let's look at the reaction and rewrite the expression, which right there it is, okay? Should I rewrite it? No. There's the expression. Kc, products over the reactants raised to the power of their coefficients. So what we need, let me grab something to erase with, what I need is a concentration of each of those guys, don't I? So let's get the concentration of each one. I need H2's concentration. Well, that would be the moles of H2, which if I look on the table there, I see that I have 4 moles of H2. And it's a 4-liter container, so I have 4 liters. And that's going to give me 1 mole per liter. All right, so we got that one. How about S2? We need S2's concentration. So we look for the moles of S2. It is 0.80. And we divide by 4 liters. This is moles per liter. So 0.8 divided by 4 is 0.2. Okay, so now we have that value. And we're going to need the H2S's value. Okay, so we got the moles of H2S, which is 1. We have a 4-liter container, so we have 0.25 molar. Okay, 1/4, which is 0.25 molar for the H2S. And now we're ready to go and obtain a value for this substance. What's it going to be? Let's plug in our numbers. H2 was 1. And that is squared, and I make sure I'm putting it in molarity. S2 was 0.2, okay? That one is, well, I'm not even going to bother writing the M because I didn't the first time. These all have to go in as molarity, but K is a unitless value. H2S is 0.25, but remember, it is squared. And when you take those values and plug them into your calculator, you're going to get a value of 3.2. So that is the value, make it right here, value for the Kc. Now, we have a couple ways that we could take Kp. But either way, we know what Kp's expression looks like, don't we? Let me grab this pen, sorry. Okay, so in a different color, we know Kp is equal to the pressure of the product, so the pressure of H2, and that is squared, times the pressure of S2, 2 divided by the pressure of H2S, and that one is squared. So products over reactants. I could go use PV equals nRT, which is nRT over V. I've got the number of moles, I got R, I got the temperature, get it in Kelvin, I got the volume. I could get each one of those and plug them in here and get a value of Kp, or I can use the expression that Kp equals Kc RT to the delta N. I think this is easier than going and getting the pressure of everybody and plugging them in there, because I've already established what Kc is. It's 3.2. I put 0.08205. It's not 5, it's 6, and that's liter atmospheres per mole Kelvin. I have to make sure I use that one. I have a temperature, 25 degrees Celsius is 298 Kelvin, and all this part is raised to the delta N. So let's look at the reaction there. How many moles of gas do we have on the product side? Well, we have 3 moles of gas on the product side. How many moles of gas do I have on the reactant side? I have 2 moles of gas. So I'm going to raise that to the first power, and that is going to give me a value of 78 for Kp. Both the 3.8 and the 78 let me know that this equilibrium has a little bit more product than it has reactant when it's at equilibrium. Now, if you want to have a little extra activity here, a little extra practice, why don't you go and verify that if you go and get the pressure for each one of these gases and plug them in, you will get the same value for your Kp. So you need to be able to take equilibrium information and obtain a K value, whether it's a Kc value or a Kp value. So in this problem, we are going to calculate, what does it say? Kp. We know that Kp for this problem would be products, that's oops, we don't want square bracket, do I? Want a P instead. So let me get something to erase with. There we go. I want the pressure of NO2, and that's squared, divided by the pressure of NO squared times the pressure of O2. So what I need to know is those 3 pressures, plug them into that expression, and I will have Kp. So we look at the information, and they're just giving me a temperature and a bunch of moles and a total pressure. So one of the things we have to draw back from chemistry, General Chemistry 1, is our gas information. And Dalton's law of partial pressure says that the pressure of a gas, and we'll call it gas A, is equal to the mole fraction of that gas times the total pressure. So we're going to use that piece of information to get all the partial pressures we need. Because we were given the total pressure, we need to know mole fraction. So I'm going to have you pause and select the answer that gives you the mole fraction of each one of those gases. Well, whoops, thought I had a little check mark that's going to pop up there. Okay, so B is your answer. All right, B is your answer, and we'll just do one of them just to make sure you understand why B is your answer. The mole fraction of oxygen, for example, would be the moles of oxygen, which I have as 0.020, and you might think, well, that's my answer. No, that's not why it's the answer. Okay, we have the moles of that divided by total moles, 0.020 plus 0.040. That is one of the gases, plus 0.96. And that is 0.020 divided by 1.02, which is a little bit less than 0.02, but to 2 significant figures, it's still 0.02. Okay, so that's that one. If you replace this with the 0.040 and then you replace it with the 0.96, you're going to get B for each one of your answers. Now we know mole fractions. So now we can take those mole fractions and we can actually do the problem. We're going to calculate the Kp. So Kp is the pressure of NO2. Well, we take the mole fraction of NO2, which I should have written them all down there. It was 0.94, okay? 0, well, actually, let me go ahead and put it into the expression. Yeah, no, that's what I'm doing. We're going to take the mole fraction, which is 0.94. And we're going to square it. We're not going to do that. That's the mole fraction. That's not the pressure, is it? Mole fraction times the total pressure, which is 0.2. Has to be in atmospheres, and it is in atmospheres. Now, all of that gets squared, doesn't it? Divided by, now the pressure of NO would be the partial pressure of NO, and we might as well back up just to verify for you guys. It was, B was the right answer, so the NO is 0.039, that's the mole fraction, times the total pressure, which is 0.2, and this one is also squared, so we will square it. And then we have the pressure of O2. The pressure of O2 is the partial pressure of O2, which was this, the mole fraction, which is this, times the total pressure, which was 0.2, and that has to be in atmospheres. This one is not squared. So when we take all of those values, plug them into our calculator, we're going to end up with a value for Kp of 1.5 times 10 to the 5th. Look at that value. What does that tell you about this equilibrium? Does it lie far to the right or far to the left? Okay, that's Kp. What if they wanted Kc instead? Could we figure out Kc from the data? Well, the easiest way to figure out Kc is to use Kp. Now we know Kp equals Kc RT to the delta N. All right, I keep the P on this side. So I have that equation, but I know this one, and I'm trying to solve for that one. So Kc equals Kp divided by RT to the delta N. Another way you might see this written is Kp RT to the negative delta N. Does that make sense? When you bring it up, it's going to be a negative sign. Okay, so let's put in what we know. We know that Kc is equal to Kp, which is 1.5 times 10 to the 5th. And then we have our R. We have to use the one that has atmospheres in it, 0.08206. And we need our T. Gives me a T, I sure hope. Yes, 430 degrees Celsius, but we don't want to leave it in degrees Celsius, do we? We need it in Kelvin. Now it's this part and this part that's going to be raised to a negative delta N. Well, delta N, we look up there at the reaction. How many moles of product do I have? 2 moles. How many moles of reactant do I have? 3 moles. 2 minus 3 is a negative 1, and then I change the sign. So I'm raising it to the first power. So I'm going to take 1.5 times 10 to the 5th times my gas constant times my temperature, and I'm going to once again get a pretty big K value. This K value is 8.7 times 10 to the 6th. Okay, unitless, but I put my units will work if I'm making sure I'm using my R value that has the atmospheres in there, and that will give me the correct Kc. So in this problem, we're going to calculate a Kc. And I'm going to teach you a very important tool. So make sure if you're getting tired, you take a break, come back, because it's very important that you watch what I do and learn a technique for solving various equilibrium problems. But when they tell me I'm trying to calculate a Kc, the first thing I would automatically do is write the equilibrium constant expression, the law of mass action for this reaction. I have as my products N2, it's raised to the first power because it's got a 1 coefficient. I have H2, it's cubed, And then I have on the reactant side NH3, so I take its concentration, and it has a 2 coefficient, so it gets squared. So I just need to know those 3 things, and I set out to try to figure out those 3 things and see if any of them are given to me. It tells me that after, it gives me a bunch of information, temperature, an initial amount of ammonia, but I put equilibrium amounts in here. And it says that after equilibrium is attained, the concentration of ammonia, that's this guy, is 0.0040. So I definitely know that bottom number, 0.0040. That one I know, but the other 2 were not given to me. They didn't give me any information about those 2, as a matter of fact. So here we go. This is our tool that's very important. I'm going to write my reaction so I can put this tool right underneath it. All right? So reactant, we've got my products of N2, it's a gas, and H2 with a 3 here, and it's a gas. Whoops, that doesn't look like a G. There we go. All right. I want to first write underneath these things how much I have initially, and I'm going to give it, all right, initially, how much am I starting with? Well, I read through there, and it says initial concentration of ammonia was 0.0240. 0.0240. If I read at the beginning, it says ammonia is placed in a reactor. That's it. That's all I put in the reactor. So initially, there aren't any of the N2 and the H2. So that's what I have initially. Okay, so then what do I have at equilibrium? Well, they tell me at equilibrium, I have 0.0040, right? They tell me how much I have there. And that's all they tell me. I am going to use this information to see what kind of change took place. The change is the reaction taking place. I'll write that down. This change is the reaction taking place. Okay, it's actually happening, the change line. So let's look, how much change occurred for the NH3? Well, if I started with 0.0240 and I ended up with 0.0040, didn't I use up 0.0200? Look at those numbers. Stop and examine those if you need to and see where I got that number. Started with this and ended with this. This was the change. Now, the reaction is taking place here. So let's look at our balanced reaction. Every time 2 of those reacts, how many of those are made? Every time 2 of those reacts, 1 of those is made. I reacted 2 of those, 0.02 of those, so I'm going to produce 0.01 of these. You see that? I'm producing half as much as I used up of this. Now look at these 2 numbers, 1 versus 3. Every time 1 of those is produced, how many of those is produced? Look at the balanced equation. Well, every time 1 of these is produced, 3 of those have to be produced. So I have to produce 3 times as much. And that would be this number, 3 times bigger than this number. So what is the amount that I will have in equilibrium? Well, if I started with nothing and I produce this amount, then I have 0.01. If I started with nothing and I produce this amount, I have 0.03. Okay? So now I know at equilibrium everything I have. Now, this is called an ICE table or an ICE table. If you can plug it in with numbers, do so. Eventually we'll see that we've got to set up with some unknowns in there and use variables. But I don't have to use variables here. I know how much I initially had, I know how much I ended with, so I know what the change is. I have to remember that the change line is the reaction taking place. Some of this is getting used up, some of this is being produced. And now I have how much is at equilibrium. So now I can get my Kc value. I look for the amount of nitrogen at equilibrium. There's nitrogen at equilibrium. It's 0.01. I need the amount of hydrogen I see the amount of hydrogen. It is 0.03, but it's cubed. It's cubed because of the 3 coefficients. So that 3 came into place twice. It tripled the amount of this versus that. Okay? It also has a cubed value there. So when we plug in all our values, I have 1.7 times 10 to the minus 2. Does this have a unit? No. I plug everything in molarity, but that is a unitless quantity. Okay, let's see what's next. I think that that's the last calculation for this one. All right, so let's remember a few things. Let's summarize a few things that we have learned along the way. To calculate the equilibrium constant for a thing, and that's what we've done a lot of, calculating equilibrium constants. You must have a balanced equation. A K doesn't stand alone. For this one, we had a reaction on the slide that this K applies with. So you have to have a balanced reaction associated with it. Here it is. Okay, I do have it written here. You would write the law of mass action from the balanced equation. You would always plug in equilibrium amounts into this expression, so usually there's a lot of work involved in coming up with these equilibrium amounts. I've showed you various things. We've used Dalton's law of partial pressure to come up with values we needed. We have used our equation for molality, moles over liters. We have used this newly discovered ice table, but you need to know equilibrium amounts before you can plug them into there. If you're going to do KPs instead, you know you have to have pressures that you plug into here, and those pressures must be in atmospheres. And then lastly, we remember that whatever we plug in, we know it's molarities or atmospheres. The value that comes out has no unit. It's dimensionless or unitless. All right, so that is what an equilibrium constant expression is, the relationship between Kc and Kp, and several examples of calculating Kc or Kp. And next we're going to learn about something that's kind of similar to K, but it's called Q. So we'll pick up with that in our next lesson.